So we're going to start chapter 15 today, and we'll finish it when we get back from break. And we're going to look at how to draw a probability histogram. First off, what is a probability histogram? Well, it's a graphical display of all the possible outcomes we could get from a chance process, when numbers are generated from a chance process, by a chance process, and the likelihood of each. For example, what's the probability histogram for just rolling a single die and counting the number of spots? All right, well first let's just translate it into a box model. So what do we have here? We have 6 tickets. 1, 2, 3, 4, 5, and 6. I'll make them circular tickets here. And now, if we want to draw the probability histogram for just one draw from this box, so we'll say just for the contents of this box, we could say just for the contents of the box, which would really be the same as for one draw from the box. So we have n equals 1. And obviously, we have an equal likelihood getting 1, 2, 3, 4, 5, 6. And so each one of those possibilities has 1/6 chance. So the way that we would draw that would be, for the histogram, we draw 6 boxes. Here's 1, 2, 6 rectangles. 1, 2, 3, 4, 5, 6. Each with a likelihood of 1/6. Because remember, in all histograms, the sum of the area has to equal 1 or 100%. And that's the same for a probability histogram as it was when we just represented just lists of numbers, not numbers that were generated by a chance process, but just lists of numbers with a histogram. All right, now what's the probability histogram for rolling a pair of dice? So let's translate that into a box model. Well, with a pair of dice, here's 2 dice. You can either think of them as rolling the pair or rolling 1, and we got a 6. And then rolling it again and adding those 2 numbers together. 6 plus 2 is 8. So for example, if you're playing Monopoly or something and you lost one of the dice, so instead of rolling 2, you could always just roll 1 twice. Whoops, 1 and then. Alright, so that's the same thing. And so there are 2 possible boxes here. If we rolled 1 die twice, then we have n equals 2, and we draw from this same box twice with replacement and take the sum of the 2 draws. So we have 1, 2, 3, 4, 5, and 6 again. All right, and now another way to think of it though is let's say we roll 2 at once. So then our possible outcomes could be range from 2 all the way up to 12. So we have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So these are the only possible outcomes for rolling a pair of dice once and counting up the spots that appear. Now, does this look right? Do you think there's an equal likelihood of getting 2 and 7? You think these are all equally likely? Or what? Well, there's only one way to get 2, right? That's if you get a 1 and a 1, so I'm just going to put a little 1 symbolizing that there's just one of those tickets. And there's only one way to get a 12, but how many ways are there to get, for example, a 3? Well, you could get a 2 and a 1, or a 1 and a 2. For example, you can think about it this way. Your first roll has 1, 2, 3, 4, 5, and 6. And your second roll would have 1, 2, 3, 36 possible ways. So there's only one way you can get 2 and one way you can get 12. But look how many different, I mean, if we say this is your first roll, and then you got a 1 in your second roll, then you'd end up with a 2, 3, 4, 5, 6, or 7. 3, 4, 5, 6, 7, 8, etc. In fact, I think we drew this before at the start of chapter 11. Let's check back to chapter 11. And that was before the exam. Yeah, here. This is what I'm talking about. There's 36 possibilities. And now, look, there's just one way to get a 2 and one way to get a 12. But, for example, to get a 7, there's 1, 2, 3, 4, 5, 6 ways to get a 7. Okay, so we actually not have just 11 tickets in here. We have 36 tickets in this box. And there's 2 ways to get a 3. That's 3, 4, 5, 6 ways to get a 7. And now there'd be 5 ways to get an 8, 4, 3, 2, and 1. And that adds up to 36. Okay, so now if we wanted to draw the probability histogram, we have to say, look at all the possible outcomes and how likely they are. So here's our possible outcomes. Well, it's really small. Let me see if I can zoom in a little bit here. Oh, it's locked. Oh, well. All right, so we could get a 2. There's a 1 out of 36 chance. So that's it, 1 out of 36. All right, so we want to draw a histogram displaying all the chances, and there's a 1 out of 30. There's 36 tickets, a 1 out of 36 chance of drawing a 2. So I have it 1 out of 36. And then there's a 2 out of 36 chance of drawing a 3, etc. So let's make this a little bit higher for a 3. 2 out of 36 for the 3. And then for a 4, etc. So we'll just draw this. Here's your 4. And 5 is going to be a little higher. There's a 4 out of 36 chance for drawing 5. And a 6 is a 5 out of 36 chance. You see what I'm doing? And here's our most likely possibility is a 7, and it goes all the way up to 1/6, or 6 out of 36. That's 6 out of 36, 5 out of 36, etc. You see? 4 out of 36. All right, that's what the scale says. And now it's just going to be symmetrical. So for drawing an 8, 5 out of 36. A 9 would be 4 out of 36. 10 would be 3 out of 36. 11 is 2 out of 36. And finally, a 12 is 1 out of 36. So that's what your histogram looks like. Kind of like a bumpy version of the normal curve. Right? Well, if you didn't draw that too well, don't worry, because on the next page in your notebook, I do it on the computer and it looks really pretty. See? It's the same thing. I just wanted to show you how to generate that. So, so here's the 2, and we said that's 1 out of 36. Same with 12. It's just expressed as a decimal here. And with the 3 and the 11, they both have equal chances, 2 out of 36, etc. All right, so that's how you draw a probability histogram for rolling a pair of dice and counting, taking the sum, counting all the spots. All right? And of course, the expected value would be 7, right in the middle here, which is the analogous summary statistic for a chance process as the average is for a list of numbers. And the standard error is, will depend, of course, hold on, so let's just do 5 out of 36 and 6 out of 36. Does that look good? All right, so that's the probability histogram. Now if you actually did this process, if you actually drew tickets at random from a box, let me show you what it would look like. So let's go to the computer, that's what I say here. that if we actually did it, the empirical histogram would get closer and closer to the probability histogram the more times we repeat the chance process. Alright, so as we saw on the previous page, that the probability histogram for rolling a pair of dice is like a bumpy version of a normal curve. And if we roll 3 dice instead, and took the sum of all the spots, so the lowest possibility would be 3, if we got all 1s, and the highest possibility would be 18, if we got all 6s, that would look even more like the normal curve. And the sum of 4 draws would be even more so. And that leads us to this extremely important theorem called the central limit theorem. And this is one of my favorite theorems in all of statistics, so let's start here. Okay, and what it says is that the probability histogram of all possible sums and averages or percentages, if it was a 0-1 box, because they're derived from sums of draws from a box will get closer and closer to the normal curve as the number of draws increases. Alright, what do I mean by that? Let's start with a really simple case, flipping a coin and counting the number of heads. Alright, so let's draw the probability histogram for the number, counting the number of heads in 1, 2, 3, and 4 tosses of a fair coin. And we'll see how the probability histogram starts looking more and more like the normal curve. So here's the box model right here. This right here would be if we got what? If we got a tail. So that's 0 heads. So 0 heads, right? And right here is if we got a head. That's 1 head. So tossing the coin translates, and counting the number of heads translates into this box model. Now, on one toss, obviously there's just 2 possibilities. You can either get a tail or a head with equal likelihood. Alright, so what does the probability histogram for that look like? Well, that's really easy. You can either get 0 or 1 head, and we have 2 rectangles here, each 1/2 tall. So this is a width of 1 times a half, so this is the area, this is a half, and the area, this is a half. And, of course, the total area of the histogram has to add up to 1. Alright, so now let's think about drawing, that was 1 toss. Alright, can I get all of this in at once? Yeah. Okay, so that was 2 to the 1, which is 2 possibilities. You could get either a 0 or a 1. Now, let's look at 2 tosses. Now there's 2 times 2, 2 to the 2 possibilities, 4 possibilities. And here they are, tail, tail. That would be 0 heads. There's 2 ways to get 1 head, and 1 way to get 2 heads. And if you wanted to draw a little table to figure it out, even though it's pretty easy to write it out, if you wanted to draw a little table, you could think, oh, after 1 toss, first it's easy tables, we're going to make it really apparent. That's what it is. And there's 4 possibilities here. So this is after 1 toss. In 1 toss, we have either 0 heads, a tail, or a head. Now, on toss 2, you could either get a tail, in which case, here we have 2 tails, here, or we'd have a tail and then a head. Or what if we got a head? If we got a head, then we'd end up with 0, 1 head total, or 2 heads. So there's our possibilities. There's 2 ways to get 1 head and 1 each. 1 way to get 2 tails, 0 heads, and 2. Alright, so let's draw that probability histogram. It's not very hard. We can get either. Our possibilities now are 0, 1, and 2 heads. And they're not all equally likely. There's only what? 1 out of 4 ways to get 0. So that should be the 1/4 of the total area of the histogram. And there's 2 ways right here. So that's half. I'll make it that tall. And then half the time you're going to get one head, and 1/4 of the time you're going to get both heads. And of course, the areas add up to 1. Okay? So now let's look after 3 tosses. What happens in 3 tosses? Well, now there's 8 possibilities. 2 times 2 to the 3rd, which is 8. And all I did was write these 4 possibilities, first adding a tail here, and then adding a head, tacking on a head. So there's 4 possibilities with the tail added on right here. Take a look at the table here and show you that this is after 2 tosses. This is what we had. 0, there's 4. I just laid those out vertically. Here's our possibility. We laid them out. And now here is our 3rd toss. Okay. So let's stick if we get a tail, we have the same number of heads, and if we get a head, we have 1 more. So 1, 2, 2, and 3. So now you can see, obviously, in 3 tosses, on the probability histogram, we can either get 0 heads, 1, 2, or 3 heads, but they're not all equal likelihood. And we can look here, out of the 8 ways, there's only 1 out of the 8 ways to get all tails. So I'll put it here, this is 1 out of 8 ways. And of course, there's 1 out of 8 ways also to get the 3. Do that too. Make it exactly the same size. And then we look here, and there's 3 out of 8 ways to get 1, and 3 out of 8 ways to get a 2. So we make it 3 times as tall for both of those possibilities. And of course, the area of the histogram adds up to 1 again, because those are all the possibilities. You can see this is starting to look, okay, let's do it for 4 tosses. It's getting tiresome, huh? Okay, so for 4 tosses, what we're going to do. So now there's 2 times 2, there's 2 to the 4th, which is 16. 2 to the 4th, which is 16 possibilities. I just took these same possibilities, these 8, and tacked a tail on, and then tacked a head on. Alright, so this is after 3 tosses. I took these 8 possibilities and laid them out here. After 3 tosses, just so you can get, this is just so you can get a feel for how the histograms can start looking more and more normal. And here's our 4th toss. Alright, so if I get a tail, I don't get any more heads when I'm counting heads, so I'll just leave this top row the same, because remember we're counting the number of heads, and then if I get another head on the 4th toss, then I'll just add 1 tallness. So I have 1, 2, 2, 2, 3, 3, 3, and 4. So now there's 16 possibilities and only 1/16, 1 out of 16 ways to get either. All tails or all heads, right? Let's do those first, 1 out of 16 ways. So on 4 tosses, you can either get no heads, 1, 2, 3, or 4 heads. And 0 heads and 4 heads are both equally likely, 1 out of 16 ways. Now, how many ways are there to get 1 head? 1, 2, 3, 4. And how many ways are there to get 3? 1, 2, 3, 4. It's symmetrical. So 4 out of 16 ways, which is the same, I'm going to get 4 times as big to get 1 and 3. 1/4 of the time, 4/16. So get either 1 or 3. So let's write 4 out of 16. Of course, the most likely possibility is our expected value to get half heads. Half heads. And how many ways are there to do that? 1, 2, 3, 4, 5, 6. So 6 out of 16 ways. Let's make it 2 units, 2 16ths taller, and we have 6 out of 16. And of course, we have 4 and 4 is 8, 6, and 2 more is 8, so 8 is 16, and adds up to 1 again. All right, now as you can see, as the number of tosses increases, do the histograms look more and more like the normal curve? Yes, they do. Yes, they do. Look at this. Yay! They look more and more like the normal curve. So, let's turn the page here. And we can do the same exact thing on the computer as we go to this website. So let's do it. All right. So, if we roll a die, we have 1. Oh, we're doing a coin, right? Let's just do a coin. That's what we're doing. So we don't need 50 to 50. Let's make it exactly like we did by hand. Okay, so our boxes starts off with a 50, we're just counting the number of heads, and here's where we start off with a 50-50 chance of getting either a tail or a head. Now, watch. Here's with 2 draws. This is the exact histogram we got. There's 2 ways to get 1 head, and so there is 1/2 of the time you'll get 1 head, and 1/4 of the time you'll get either all tails or all heads, and we got up to here 4 draws. This is just what it looked like. And if we went on to 5 draws and 6 draws and more, watch. It's going to look more and more like the normal curve. Isn't that beautiful? Isn't that really pretty? Look at that. Just more and more and more like the normal curve. Here's 100 draws. You can see that 50, you expect to get 50 heads. Right in the middle, that's the expected value. Here's the average and the standard deviation. So the expected value is standard error. And theoretically, you could get 100 heads. It's just such a tiny possibility that it's not on here. And you could get all tails. Equally tiny, tiny possibility, because how many different possibilities are there? With 100 draws and 2 to the 100th ways. Which would be like what? 1.27 times 10 to the 30th. You couldn't possibly write down all the different combinations like we did with 4 draws. All right, now the most amazing thing about what the central limit theorem says is no matter what box you start off with, like you could have, you could have a really lopsided box. You could have a 1, 0, 1, 1, and you could have, I don't know, whatever you want. Something really lopsided. 237 what? I want to say 3s. Something really crazy like that. But look what will happen. With enough draws, it doesn't look at all like the normal curve now. It still doesn't. Still doesn't. But watch what's eventually going to happen. It'll take a long time with such a lopsided box. But with enough draws, the probability histogram with the sum of the draws is going to start to look normal. Look at this. It's going to take a long time because I have such a weird box. But do you believe this? I think it's going to start I know it's going to look more and more normal. Let's see how long it starts to take before you can believe me. Where are we at? 2. See, it's getting a little more normal. Look at this. Isn't it kind of getting prettier? Prettier? Look at this. Takes a lot of draws, but we can count on it. That's what the central limit theorem says. That with enough draws, I don't care how weird, how unnormal, how lopsided your original box looks, the probability histogram for the sum of the draws will eventually look like the normal curve. Oh, it's so beautiful. This is so comforting to me, especially because it's the reverse of a recurring nightmare I used to always have as a child. Whenever I had a fever, I would start with something really tangled and disorganized and really unnormal. And I would spend all this time making it look beautiful like this, and just as it was about to reach normality, like this is about to do, instead of it continuing like this is going to do, it would start disintegrating and getting all weird and ugly looking. And this will never do that because of the central limit there. Look at this. Oh, it's so beautiful. I just want to go a little further and we'll see. Do you believe me now? Look at that. We'll just go to 1,000. Wow, so pretty. All right, I'm back to our notebook. All right, so we'll go back to the document camera, and we can illustrate this point that, first of all, regardless, this is what I want you to look at, regardless of the contents of the original box, with a large enough number of draws, the probability histogram for the sum, the average of the percent, will follow the normal curve quite closely, which is going to be amazingly useful because we're going to be able to substitute the normal curve for the actual probability histogram as long as we have enough draws, so we'll be able to figure out the chances of real easily, the way we did with descriptive data. But remember, with our descriptive data, we had to, what do I mean descriptive data? When we actually had a whole bunch of data in front of us, we could only use the normal curve when the actual data looked like the normal curve, like for height, for weight, for IQ. We couldn't do it when we had data on income, on money, on the number of pairs of shoes people own. They were highly skewed, so we could never substitute the normal curve to figure out the percentage of the people of the data that fell within certain intervals. But with a chance process, like public opinion polling, drawing 1,000 people randomly from the whole nation, we can use the normal curve. Now the question is, how many draws is large enough? Well, as we saw, that depends on the contents of the box. The more the histogram of the contents of the box differs from the normal curve, the more draws are needed before you can use the normal approximation is what I want to say here. All right, now consider two boxes, 1, 2, 3, and 1, 2, 9. Now let's draw the histograms for just one draw for the contents of the box. Do you see how this one's going to look more symmetrical, more normal than this one? Watch. For this one, we have 1. We can get a 1, a 2, and a 3, all with equal likelihood. So we'll just draw 1, 2, 3. And all of these blocks will be 1/3 high. All right, add up to 100. Now for this box, we can get what? A 1, a 2, a 3, a 4, a 5, a 6, a 7, an 8, or a 9. No, that's not what we can get. We can only get a 1, a 2, or a 9. A 1, a 2, or a 9, all with equal likelihood. But since it's a histogram, we have to draw the horizontal axis to scale. So I can't draw it more. I can't just substitute the 9 right here and say 1, I can't say 1, 2, and 9 and make the histogram look the same way. All right, so now we have 1, 2, all the way up to 9, and the first two blocks are going to look exactly like our histogram on the left. A 1/3 chance for each. But now, look how far out the 9 is. There's a lot more variability inside the box. All right, and there's a 1/3 chance for each. Now, let's draw the histogram for the sum of two draws from each box and see what they look like. And you'll see that this one's going to look a lot more normal than this one because it starts off looking more like a normal curve. All right, so let's do it. So if we drew twice from this box, we can either get this is our first, it's a table again, just like we did before. Let's say this is our first draw. Let's say we've got a 1, 2, 3, then we replace it, and we can get a 1, 2, 3 next time. So there's 9 possibilities. This is n equals 2. There's 9 possibilities because it's 3 times 3. So what can we get? Well, we've got 2 1s, 2, 7, 3, get 2, 3, 4, 3, 4, 5. We can get first a 1 and then a 3, that would give us a 4, a 5. And the highest we can get is if we've got 2 3s, and that's a 6. All right? So we can draw the probability histogram for that. And let's do that. And what can we get a 1? No. 2. We can get a 2, and what's the likelihood? There's 9 possibilities. 3 times 3 squared is 9 possibilities, and only one of them is a 2. So it's going to look like this. And it will be 1/9. All right? How about for a 3? Well, there's 2 out of 9 possibilities. So let's make it twice as tall. It should be the same width, and that's 2 out of 9 possibilities. And for a 4, there's 3 out of 9 possibilities. So 3 out of 9. And it's symmetrical, see? 2 5s and 1 6. 5 and 6. Alright? And right in the middle here is our expected value for the sum, would be 4. N times the average, 2 times the average of the parts, which is 2. The average box is 2. Alright, now let's look at this. There's still n equals 2. We're doing 2 draws from that box. There's still 9 possibilities. And let's see what they are. Alright, if we add 1, let's say we could get a 1, 2, or 9. We're looking at so if we got a 1 the second time, and we added the 2 numbers together, here we get a 2, a 3, and a 10. If we got a 2 the second time, add a 2 to each of these numbers, we get a 3, a 4, and 11. Or we could get a 9 on the second one. We get a 9, 11, and we got 2 9s. The largest the sum of the 2 draws can be would be an 18. All right, so now let's draw that histogram. And again, there's 1 out of 9 possibilities. And there's only one way we could get a 2. That should be 1/9 high. There's two ways we can get a 3, so that's 2 9s high. One way we can get a 4, so that's 1/9 high. And then we skip all the way to 10 and 11, and both of those have 2 ways, so they should be 2 9s tall, both of them. 2 out of 9. 2 out of 9, so you can see that's how tall those 2 are. And then there's just one way we can get an 18, so that should just be 1 out of 9. So this is 1 out of 9, 1 out of 9, and this is 2 out of 9. So we have 2, 4, 6, 7, 8, 9, 9 out of 9, and it adds up to 1. But you can see that this becomes normal much sooner from this box. And this will take more draws before the histogram, probability histogram begins to look normal. Whereas this one, look, it's almost normal already. Okay? You got it? let's see how long it takes for this one to get normal as opposed to this one, okay? So let's go back to the PC, and we can choose a box. And our first box was, we can look at that one, we had 1, 1, 2, and 1, 3. Right? We accept the box, and this one's going to get normal really fast. Watch. This is what we did, and look. You can see. Look how pretty that is. Already, it's pretty normal. Now, let's choose a different box. Let's choose 1, 2, and 9. That's our second box. Accept the box. That was our original histogram. Now we do histogram of sums, and this is the one we did. Right? There's 1 out of 9 ways to get 18. Here we have 2 out of 9 ways to get 8 times 11. Doesn't look normal right away. Look. It takes quite a while. See all those spikes? But look. Hold on. Still see all those spikes, even at 50. Let's keep going. But you can see that this one doesn't take that long to get really. Alright. And here's the expected value, or the average of the box is 400, and 100 draws, because, I mean, the average of the sum of the draws, the expected value of the sum, 100 draws. It's 100 times 4, because the average of the box is 4. Alright, let's go back to the document camera. And front page. Alright, let's do this problem. This is just an illustration of what we just did on the computer. Here it is. Look at the probability histogram for the sum of 25 and 50 draws from these two boxes. These tickets and these tickets. See what I was doing? So the average of this box is 2, and the average of this box is what? 12 divided by 3 is 4. So, right in the middle, these numbers right here, I don't know if you can see them. Let me see if I can zoom in. But this would be the expected value for the sum of 50 draws, which would be 200. That says 200 right here. Can you see that? And here's 100. And from this box, right in the center here is the expected value for the sum of 50 draws would be 2 times 50 is 100. Oops. For 25 draws is 2 times 25, which is 50. And here's for 50 draws is 100. N times the average. Okay. And if you computed the standard deviation of each of these boxes, which we haven't done, but which we could easily figure out, you would have to, the standard deviation, this box, see the standard error here? Oh, it's so hard to see. Can we zoom in? Hold on. Zoom in, what does that say? The standard, this is the standard error for the sum of the draws. So this right here is going to be the square root of n, which is about 7 times the standard deviation of the box. Oh, here, let's do this one. Square root of n is 5. So it's going to be 5 times. So if we divide this by 5, about 4/5 would be the standard deviation of that box. All right, let's move on and let's zoom out. That's in. Out. All right. Let's just do 2. Aren't you tired? I'm getting tired. All right. So let's just do a few more examples, and then we will be done. So, let's do this example. 25 draws are made with replacement from the boxes below. One has 1, 0, 1, 1, 9 zeros and a 1, and 24 zeros and a 1. Okay? Now, the probability histogram for the sums of the draws are shown below. 25 draws. And you don't have any horizontal axis marked. So you can't just look at what the expected values are, you have to look at the shape of the histograms. And you want to match the probability histogram for the sum of 25 draws to the boxes. So, let's look at this. Now, this looks the most normal to begin with. And this is the most lopsided. Most lopsided right here. This one. You see it has 24 zeros and 1 1. So that's really lopsided. And this one is, right here, is the most normal. Most symmetric. Most normal. And then you look at these histograms. Which one is the most normal? This one, right? So wouldn't that correspond to 25 draws from box A? And which one's the most lopsided? This one. So this would be C and this would be B. Okay. Alright, let's look at the next question. Below are the probability histograms for the sum of 100, 400, and 900 draws from a box that has 99 tickets marked 0. Whoa, huge amount of zeros. Here would be the probability histograms of just one draw, or the contents of the draw would look like. That would be 0. And just one, what is it? Just one little one. Very lopsided. So it's going to take a long time before it gets normal. Alright. So which histogram is which? Well, you see how this is going to be 100 because it's the least normal looking. And this will be for 900. And that's for 400 because this one is the most normal looking. It's just going to take a long time because we have such a lopsided box. We have 99 zeros. 99 of those, only 1, 1. So this is the most normal looking. Okay, and next time what we're going to do is we're going to use the normal curve, the normal approximation, to figure chances for all the gambling games that we've been doing. All right? The chance of winning a certain amount of money or losing a certain amount of money and all the different gambling games we've been doing. Okay, so that's for after break. See you. Have a great break.